So today we're going to be doing 9.9, which is graphing rational functions. So there's a lot of different rules you need to know about graphing rational functions, but the good news for you all is these are open notes tests, so you get the hang of it, and then you can apply these procedures. So there's really three main ways that these can go: bottom heavy, top heavy, or same. When we talk about heavy, we're talking about the degrees, okay? So what I mean by top heavy is the degree of the numerator is larger than the degree of the denominator, okay? So like this is like x squared and this is x. That's top heavy. The same would be if the degree on the top and bottom is exactly the same. So for example, if it's just x to the first over x to the first, that would be the same. And then bottom heavy would be if we're in a situation where this is an x on the top and maybe an x squared on the bottom or an x to the third on the bottom, that would be what we consider to be bottom heavy, okay? Now, as for how that affects the graph, it actually affects the horizontal asymptote. If the graph is top heavy, we don't have a horizontal asymptote. If it's bottom heavy, it's always y equals 0. And if it's the same, it's a divided by b. Now, what is a and b? A and b are the coefficients of the x. You all know what coefficient is, the number that comes in front of it. So you divide the numerator coefficient by the denominator coefficient. Oftentimes they won't have a coefficient, so what is the implied coefficient? 1. So it's like 1 divided by 1, which oftentimes is going to end up being y equals 1. Now the next topic we need to talk about that's very important. In this class, in many math classes you take after this, if you're going on a calc track, you're going to hear continuity, discontinuity a lot, and if you go into statistics, you're also going to hear it in application. So let's talk a little bit about what that means. If I draw a graph, okay, and I can go from one side of the graph to the other without lifting my finger up, that means that it's continuous, okay? So if I stay on the graph the whole time and there's no holes in it, there's no asymptotes, anything like that, that would be a continuous function, a continuous graph. Discontinuity can occur in many ways, but the two ways we're going to talk about today is via vertical asymptotes and holes, okay? So a literal hole in the graph looks something like this. All right, so it's a spot where that graph just doesn't exist. And this occurs when you have something that cancels out. So you see how we cancel out the x minus 2's? When that happens, that means that we have a hole in the graph where that x value was. Okay, we removed it. Those are based on our restrictions. You all remember how we find restrictions by setting the denominators equal to 0. Now, a vertical asymptote occurs where we have a denominator that we set equal to 0 to find its restriction. That will create a vertical asymptote. So it didn't go away, but it's a restriction. Okay, restrictions that are removable versus non-removable. So you're going to see in application how this all works. Now, to remind you all, I'm going to try my best to make everything accessible and visible here on my screen as I can as we go through it. But we only have one screen, and I'm working with a lot of different, I'm working with Desmos and trying to zoom in and out for different sections, so just bear with me. At the end, I'm always going to show the whole thing so you can get it down if you missed it, all right? So the methodological approach to graphing these, first you identify if it's bottom heavy, top heavy, or the same. Then you factor if necessary. And then you find any points of discontinuity, all right? And then from there, we start working with Desmos, okay? Oh, and our asymptotes if we have any, which are going to be found through those methods. So I'm going to zoom in here so we can take a closer look. First thing I do is I look at this and determine if the degree is bottom heavy, top heavy, or the same. What do you think?
Bottom heavy.
Same.
Same. So the top heavy, bottom heavy is only based on the degree of the variable, okay, not the numerical part. So its degree is 1 over 1, which is the same, okay? So it tells me that if they're the same, my horizontal asymptote is y equals the coefficient of this x divided by the coefficient of this x, which is 1 divided by 1, which is 1. That's that. Now, in this particular equation, is there anything we need to factor here? No. Is there anything that cancels out?
No. No.
No. So there's no hole. is there a denominator that we have to set equal to 0 to find a restriction on? Yes. So we take that denominator, we set it equal to 0, and very good, we solve for x, and x is equal to -2. That whole equation is going to be your non-removable vertical asymptote. It's always going to be x equals your vertical asymptote, okay? Horizontal asymptotes are y equals, vertical asymptotes are x equals. Now everything else we can find based off of the graph, okay? So we can kind of wait on all these. Now to find intercepts you can always plug in 0 for the opposite variable, but Desmos can do that work for us, so let's take a look.
Why choose the bottom one?
Because we can have 0 in the numerator, we just can't have 0 in the denominator. So you always set the bottom equal to 0. So I'm going to type in the equation. Now here's an important tip for you all. You're going to want to put that top in parentheses. Because what's going to happen if you try not to, so say I don't put it in parentheses, watch what happens. So I do x plus 4 and then I try to do divided by it, you see the problem? You have to put it in parentheses so that it does the whole entire thing in the numerator, okay? Yes?
It's x minus 4.
Ah, thank you. Okay, so this is what my equation looks like. Now I'm going to go ahead and put in my asymptotes, which are right here, and you can confirm those visually as well. Now looking at this, I want to find my intercepts, so I look at where my graph crosses the x and the y-axis. So everybody see those 2 points. Okay, so those are my intercepts. So I'm going to write those down here. Okay, so we have an intercept at 0, -2, and at 4, 0. So now I'm going to zoom my graph out so I can actually graph this myself. So the first thing I always graph is my asymptotes. So I have one at 1 for the y. And then I have, oops, that wasn't that good. It's hard on this graph. I can actually zoom it in so we can see it better. I have one at 1. Eek, I can't get this right. Okay. And then I have one at -2, right? Is that where it is? Yeah. -2. And then I'm just going to start by plotting my intercepts, because that's a good place to start if you have some. And then I want to pick some value in the middle of these two. So it looks like I have a point at 1, -1. So now that I have about 3 points, I can connect this and get a general idea of what it looks like. And then on the other side, I'm going to want to put in my table maybe like -3, -4, -5, something around here that's going to give me the other side of my graph. So you all remember how to manipulate the table. We've been practicing this for a few days. So -3, -4, -5, I manipulate my table on Desmos. So -5 is at 3. -4 is at 4, and -3 is at 7. And then I can just connect these, and you always want to make sure that with these type of graphs that they look visually symmetrical. So now that I have a general idea of my graph, I can zoom out and I can actually start finding the rest of my classifications and whatnot of my graph. So as for my domain, this function, it takes on every x value in existence going off to the left and going off to the right, except for one x value that my function doesn't take, which is what? -2. So there's 2 ways you can write this domain. I'm going to teach you both. So you all remember the way we wrote it yesterday, right? This is sufficient, but I want to show you an alternative because you'll see this done more often because it's easier. So sometimes in math, we assume that the domain is all real numbers with some exceptions. Okay, so that's sometimes an easier way. So like if I were going to tell you you could pick any number out of 100 except for 99, would it make more sense for me to just say don't pick 99, or should I list out all the numbers you should pick? You know what I'm saying? So that's sometimes where we go the other route. So x such that when you see this terminology in math, this means that they're talking about the whole entire real number set. They're saying x can be anything, except for x cannot be -2. So that's a way of saying what x is not instead of saying what x is. Does that make sense to you guys? Okay. And then we can do the same thing for the range. X can be any, or y can be anything except for what? Very good. It exists everywhere, it goes up forever, it goes down forever, except for that one spot where it takes on its horizontal asymptote at 1. And then of course we always look at end behavior. With these particular graphs, the end behavior is going to be pretty consistent. It just approaches what value on both sides? It approaches the asymptote, right? The horizontal asymptote, which is at what value? 1. Alright, so what do you think so far about this one? Did you understand all the steps? Okay, let's try another one. We're going to do an example of each type, top heavy, bottom heavy, same. So that's kind of the goal. Alright, so the next one we're going to look at, first thing we're going to do is we're going to determine if it's top heavy, bottom heavy, or the same.
Top heavy.
Top heavy, very good. So it's top heavy because the degree of the numerator is larger than the degree of the denominator, okay? So, bless you.
Wait, what was the end behavior for number 1?
It was 1 and 1 for both of them.
Okay.
So, oh, yeah. What does the notes say if you're top heavy, what your horizontal asymptote is? None. Very good. We don't have one if it's top heavy, so that's cool. One less thing to worry about. Now the next thing you need to do is make sure this thing is factored, and unfortunately this one is not factored as much as possible, so we are actually going to finish factoring it. So how can I factor the numerator? Very good. Factors of -3 that add up to 2. Okay? So what we would do now is we would find our restriction in the denominator. So we set this denominator equal to 0 and we solve. And we're going to hold on to this because we don't know yet if this is removable or non-removable yet. But
Shouldn't it be? Because there's something to cancel it out.
Exactly. So we found our restriction. Now we're going to determine if it is removable. And does everybody see how this one is removable? Do you all see that? Okay. So what's going to happen is this is just going to end up being x plus 3. But, of course, we didn't have any non-removable vertical, but we did have a removable of 1. So we didn't have one of these. This only exists if you have a denominator left in your function, okay, when you're done with this canceling. Do you see how there's nothing left to have a vertical asymptote for? Everybody got that? Okay. So, how do you find the y-coordinate of your removable asymptote? Well, what you do is you simply take the new function and you plug that value in for x to get the y, which comes out to be 4. Very good. And I'm also going to show you how you can confirm this on Desmos as well. So does anyone have any questions so far? So anybody know what kind of classification this function is right here? Is it quadratic? Is it linear? Is it exponential? Linear. It's a linear function, okay, with a twist, okay, because it has a restriction on it. So if I pull up Desmos here, why is it pulling up? Oh, it's pulling up on the other screen. Yeah. There we go. So when I do this, I actually prefer to type in the original version of the function prior to us canceling stuff out, and you're going to see why in a second. I don't know why I keep hitting enter instead of this division button today. There we go.
I did that yesterday a lot.
Yeah, I keep hitting enter and I'm like, what the heck? So annoying. So anyways, you see how it just looks like a linear function? Even though it looks more complex? That's because technically speaking, these are just going to cancel out, right? So it's really just x plus 3. But the reason that I put this in is because now Desmos has information. See that? Now Desmos knows that there's a restriction at the 1. If I just put the function in without that denominator, which will be the same function given, right? See how Desmos doesn't know about that restriction. Versus when I do put it in, now I've given Desmos the algorithm information to tell me that I have that hole in the graph. Do you all see the difference there?
Yes.
Okay. So either way, you're going to get the same answer as long as you know where to find that hole. But I like to get as much information as I can. So I go to the table, but do we really need a table to graph this? No. This is just a linear function with a y-intercept of 3, okay, and a slope of 1, right? So 1 over 1, up 1 over 1. But like I said, just like any other function, you can definitely use the table if you want. But am I going to put a regular circle? Oh, I graphed it at 2, not 1. That's my bad. We're in a basketball game right now. So, am I just going to put a normal circle right here?
Open circle.
Open circle. So that's like the main difference. And Desmos will do all this work for you if you want. Okay. But sometimes it's easier to just do it on your own if it's this simple, right? So I just connect it. I don't have any asymptotes to worry about, so that's good. So to the best of your ability, it's going to look something like this. Okay. All right. So, do we have any x-intercepts here?
X equals negative 3.
Very good. And do I have any y-intercepts?
Yeah. 3.
Regular 3. Very good. So, if we look at a regular linear function, what's the domain for any regular linear function?
Negative 3.
Good. This one is close to that, but what's that one restriction on it?
1.
Good. X cannot be 1. And what is the range of a normal linear function? Same thing, but we have one restriction. Y cannot be
4.
4. Range is based on where the y's are going. Domain is based on what the x is doing, okay? Everyone understand where I got those two numbers from? Okay. There's going to be times where we have both asymptotes to worry about and removable holes. Okay, so I'll talk about that too. Now, this is what the function's doing at the end and beginning of its lifespan. Okay, even though it's infinite, it lives forever. What's this function doing over here?
Decreasing.
To negative infinity. It's going in a trajectory, a direction. It's going somewhere, right? And then up here, it's going
Positive infinity.
good. So are you starting to see the difference between graphs that approach numbers versus graphs that approach infinity and negative infinity? Visually? Okay. Because that's something that you want to start being able to identify at this level. Alright, so the next one we're going to do is this one here. First thing I do is I determine, is it top heavy, bottom heavy? What's going on with this one?
Bottom.
Good, this one's bottom heavy. Does everyone understand why? Okay, the degrees, of course. Degree on the top is smaller than the degree on the bottom. So what does that mean about our horizontal asymptotes? Very good. So if you're bottom heavy, your horizontal asymptote is y equals 0. Next step is you're going to factor this. So what do we notice about the denominator and how it factors?
X plus 2, X minus 2.
Very good. X plus 2 and x minus 2. Now we set those denominators equal to 0, and we have to solve for both of these, right? So if I solve this one over here, x is, and over here x will be good. So now we have to determine which one of these is removable, which one is not. So what can I cancel out of the top and bottom of this?
Negative 2 and 2.
Good,
Oh.
which leaves me with this, right, as my new function. So this one right here is the removable one. You see that? We don't know what the y-coordinate is, we'll get there. And then this one here is the non-removable one, because it's still there. Does everybody see the difference between the two?
Yes.
Okay. Now, to find where that hole actually exists, we take the new function and we plug the hole in for x, which gives me y equals negative 1/4. Make sense to everyone? Okay. Now, like I said, you can in Desmos you have the choice of graphing this as the original, because then it will show you where the holes are. But if you graph it as the new function, it's still going to look the same. It's just not going to put those holes in there. So we have y equals x plus 2 over x squared minus 4. And if you put the factored version, it's going to look the same. Okay, it doesn't change the graph. And then we have a horizontal asymptote at y equals 0 and a vertical one at x equals 2. So first and foremost, I'm going to go ahead and graph those asymptotes. So I know I have one at 0. And I also know that I have one at 2. Like that. So from here, I can use my table to get values. So it looks like I have an intercept at 0, negative 0.5, which is right here. So does everybody see how that is my y-intercept? And I'll go back to the graph, don't worry. 0, negative 0.5. Now, is it possible for me to have an x-intercept here? No, why not?
Asymptote is 0.
Very good. So we know we don't have one of these. Okay. Now I'm just going to use the table function on Desmos to allow me to come up with some values. So it's going to look something like this, okay? And I'm just going to put some values in. So I have a point at 1, negative 1. And now I kind of see where this is going. I have a point at this spot here, but here's the problem. We know we have a hole in the graph somewhere, right? Where do we have a hole in the graph? At negative 2, right?
Yeah.
Negative point. We have a hole right here. So it's going to be really hard to draw because see how we have that big asymptote kind of in the way of drawing it? So try to just draw it the best you can to indicate that it's a hole. And if you ever want me to know that you have a hole but you can't really see it, you can always just put a little arrow and say hole. I've seen that done before. I used to do it on my own tests because I was paranoid that my teacher wouldn't see it. So we have a hole right there. And then as for the others, looks like we have a point at, let's try 3. Yeah, 3, 1. And then we have a point at 4 something. 4.5 or 4, 0.5. And then it's like this, almost like to the, it's gonna look something like that. Any questions about that? Now here's where the domain and range are a little bit more tricky. X can be anything except for what?
0.
0's okay.
Except for negative 2, positive 2.
Very good. X cannot be negative 2, and X can also not be positive 2. Because that's my vertical asymptote and my hole. You see that?
Oh, that's
And then Y can be anything except for what?
negative 1/4.
And also
Positive.
0.
0. So domain and range exclusions are based on vertical asymptotes and holes. okay? Sometimes you have one or the other, sometimes you have both, sometimes you have none. So if that helps you, feel free to write that down. Domain and range exclusions are based on vertical asymptotes and holes, okay? Anything y related is going to be dealing with the range. Anything x related is going to be related to the domain.
Wait, what's V.A?
Vertical asymptotes. So you all understand that statement, what it means? Okay. And then end behavior. Is this function ever approaching any type of infinity on the y?
No.
It's just getting closer and closer to the?
0.
Good. The asymptote, which is at 0. So anytime your graph hugs like an asymptote like that, those are going to be your end behavior. Make sense? Okay. So my goal with